It's crazy that every second you use your smartphone, there is a chemical reaction, like a baking soda volcano happening inside of it. It looks like a solid device without many moving parts, but it's true. Inside the battery, there is a chemical reaction that is continuously running, and without it, your phone would just be dead, which is something we're all familiar with. Let's investigate this lithium-ion battery. How does it power your smartphone? What happens when you recharge it? And probably what we're all wondering, why does your battery die earlier and earlier in the day? To answer these questions, let's open up this battery and look inside. So first, how does your battery power your smartphone? Let's start from what we know. All batteries have a positive terminal and a negative terminal and supply power or electricity to our portable devices. So electricity is essentially a flow of electrons in our smartphone. Electrons which are negatively charged flow from the negative terminal and run things like the speakers or the display, and then end up in the positive terminal. So then, where does this flow of electrons come from? Well, this is a lithium-ion battery, so the electrons come from the element lithium. At the negative terminal, which is technically called the anode, lithium is stored between layers of carbon graphite, similar to the graphite in your pencil. Graphite has a nifty crystal structure of layered planes that allows the lithium to be wedged in between each of the layers. The technical term for this is intercalation. Graphite functions as a kind of like stable storage space for lithium atoms. Okay, moving on. One inherent property of the element lithium is that it doesn't like its outermost electron, and it wants to give it up. When there is an available path from the negative terminal to the positive terminal, this electron separates from the lithium and starts heading to the other side. At the same time, the lithium leaves the graphite and becomes positively, or +1 charged, and is now called a lithium ion. FYI, an ion is just a fancy word for an atom who has lost or gained an electron and thus is charged. When a lot of lithium atoms leave the graphite at the same time, a flow of electrons is built up. So, let's now jump to the positive terminal, which is technically called the cathode. Here we have cobalt, which has lost some electrons to oxygen, thus making the cobalt positive, or +4 charged. As a result, it wants to gain back an electron. So when we connect the negative and positive terminals to our smartphone, the electrons flow from the lithium, which wants to give up an electron, through the circuits and components in the smartphone, and to the cobalt, which wants to gain an electron. Now here we run into a small issue. With the flow of electrons from the negative to the positive terminal, the cobalt side grows more and more negatively charged, and the other side positively charged. Yes, the electrons do want to flow in this direction, but at the same time, electrons don't like to flow to an area that is growing more and more negatively charged. This is because opposite charges attract and similar charges repel. So to fix this, we give the now positively charged lithium ions that recently left the graphite a path to move to the other side. This path is called an electrolyte, and its function allows for the lithium ions to migrate over from one side to the other, while not allowing the electrons to move through it. When lithium gets to the cobalt side, it again wedges itself or intercalates with the cobalt and oxygen to become lithium cobalt oxide. The lithium isn't regaining its electron, that electron went to the cobalt. It's just balancing out the charge buildup. Let's quickly recap. Here is a full battery. Throughout the day, lithium atoms leave the graphite layers and separate from their electrons to become lithium ions. The electrons flow from the negative terminal through the circuits and components in the smartphone and into the positive terminal to join the cobalt atoms. At the same time, the lithium ions travel through the electrolyte in order to neutralize the charge buildup and keep the reaction going. Here's the chemical formula for the reaction. Thus, at the end of the day, almost all of the lithium has left the graphite layers and joined the cobalt to become lithium cobalt oxide, and your battery is now running on empty. Now that the battery is empty, let's recharge it. We plug in our smartphone, and when we do this, The USB charger applies a higher force on a flow of electrons in the opposite direction. Electrons are pulled out of the cobalt, thus returning cobalt to its +4 state and kicking out the lithium ions. On the other side, electrons are forced onto the graphite, which pulls the lithium through the electrolyte and back into the layers of graphite. As you see, it's the exact opposite of the earlier reaction, which is why this battery is rechargeable. The lithium and its electrons move in one direction when you use the phone, and the opposite when you charge it back up. Okay, so now let's rewind and add a few more details of note. First, these two sides can't touch. If the anode and cathode were to touch, and if there were any lithium left in the graphite, the chemical reaction would accelerate uncontrollably and cause a fire or often a small explosion. Thus, a non-conductive semi-permeable separator that allows the lithium ions to pass through is placed in the middle. And this electrolyte isn't an effective barrier because it's a liquid. The second thing to note is that the graphite and cobalt peroxide aren't good at collecting or distributing the electrons. Thus, a conductive copper layer is added next to the graphite, and a conductive aluminum layer next to the cobalt peroxide. These two layers, or sheets, are called collectors. Okay, on to third. These animations are showing 100% of the lithium moving from the anode to the cathode and back. But in reality, there will always be some percentage of lithium that remains in the anode, cathode, and electrolyte, despite the battery being fully charged or discharged respectively. Continuing to fourth, in order to maximize the capacity of the battery and allow the battery to fit in your smartphone, all these layers are folded and wrapped into a rectangular prism package. I know this is a lot, but fifth and final. In order to regulate the flow of electricity, additional circuitry is added to the top of the battery. This circuitry prevents overcharging and damage to the battery. So then the final topic. Why does your battery's max capacity reduce over time? There are several reasons, one of which is that sometimes lithium and the incoming electron react with the electrolyte and organic solvent to form compounds that are called solid electrolyte interphase, or SEI. SEIs irreversibly consume lithium and the electrolyte, thus reducing the overall quantity of lithium and thereby reducing the max capacity of your battery. Another reason is that when you fully discharge your battery until it's dead, it can result in too much lithium on the cobalt side, which causes the irreversible generation of lithium oxide and cobalt-2 oxide. These compounds are stuck in that state, which thereby reduces the amount of lithium and cobalt for future use. So one tip is to not let your battery run until it's empty. It's better to recharge your battery at 30 or 40% than to let it run until it's dead. That about wraps it up. When it comes to batteries, there are hundreds of different chemistries and compounds that allow them to work, but they all work on similar principles. You just need 3 materials, one that wants electrons, one that wants to give up electrons, and then a path for the buildup of charge to neutral.